This is the screencast for section 5.2, example 2. We're going to prove identities. So in other words, the problem gives you that the tangent of x plus cotangent of x equals secant of x cosecant of x. They're telling you that is true, and you will assume that it is true. You just have to show that the left side does equal the right side. As I mentioned in example 1, you need to pick which side you're going to work with and only work with that side. You can't touch the other side. So, which one seems more complicated to you? There's really no easy answer to that. These two look very similar to me in terms of complexity. I don't like working, I think the plus sign is more complicated, so I'm going to, in this one, work with the plus sign first. That does not mean that it won't work working with the right side first, but I am going to choose to work with the left side first. So on the left side, tangent of x plus cotangent of x. I don't really see anything to do with this yet. I know that my end result is not supposed to have a plus sign, so, and then there's secant and cosecant in there, and tangent and cotangent on this side, so that is starting to get confusing. I'm just going to change everything to sines and cosines and see if that lends me a direction to go. So tangent of x is sine of x over cosine of x, and cotangent of x is cosine of x over sine of x. Make sure I put my equal sign off to the right to show my grader, me, that I'm only working with the left side all the way down. Now they do not have a common denominator, so I'm going to write sine of x over cosine of x times, and I'm going to give this guy a sine of x in both the numerator and denominator, plus cosine of x over sine of x, and I'm going to give this guy a cosine of x. So the common denominator is sine of x cosine of x. So now I've got sine squared of x plus cosine squared of x all over cosine of x sine of x. Interesting. Sine squared plus cosine squared of x is 1. I know that from my Pythagorean identities. And this is really just 1 over cosine of x times 1 over sine of x, which is secant of x times cosecant of x, which is exactly what I was supposed to prove. Secant of x cosecant of x. So I have proved that identity. The now try problem number 13. Oh, which side are you going to work with? Now in this, in my opinion, both of these sides have equal complexity, so it just depends. Do you want to work with something that looks like this? Does that give you an idea of how to start right off the bat, or does this side give you an idea of how to start off right off the bat? Now, I have shown you how to do this problem both ways in your notes, but for the case of the screencast, I think the left side shows you right away what you can do. 1 minus tangent of x squared means 1 minus tangent of x times 1 minus tangent of x. So that gives me at least a direction to go. I'm not really sure yet if it's going to get me anywhere, but I can give it a shot. So now if I multiply all that out, I get 1 minus 2 tangent of x. Oh, interesting. 2 tangent of x minus 2 tangent of x. I'm keeping my end in mind, and I see this is something I'm going to need later. And then plus tangent squared of x. So I have a minus 2 tangent of x. So I'm gonna rewrite this because I have my minus 2 tangent of x last. Now this first part is supposed to look like secant squared of x. Turns out 1 plus tangent squared of x, just by like my Pythagorean identity, is secant squared of x. So secant squared of x minus 2 tangent of x is secant squared of x minus 2 tangent of x. I have just proved that the left side can equal the right side. Now I've chosen to show you another problem for this example, number 30. Very similar situation. The left side, though, isn't quantity squared, it is tangent squared minus sine squared. The right side is tangent squared theta times sine squared theta. I'm going to work with the side that doesn't have the subtraction sign this time, just to change it up a little bit. So on the right hand side here, I have tangent squared of theta times sine squared of theta with no subtraction, and I'm trying to get the subtraction version of those same two trig pieces. It's so weird. Well, I don't really know what to do yet, but I do know that tangent squared is sine squared theta over cosine squared theta. So I'm going to leave sine squared theta alone. I am trying to get a subtraction sign. I know that sine squared is 1 minus cosine squared theta. So I'm going to do sine squared theta over cosine squared theta, and I'm going to multiply by 1 minus cosine squared theta. Now see, what's nice is I can see that I have a cosine squared in the denominator that is going to cancel out with that once I distribute this in. So I am going to do that. I'm going to distribute this in because I'm not really supposed to have a cosine per se on the left side, my end goal. I'm supposed to have a sine over cosine squared. So when I distribute, I get exactly what I wanted. Sine squared theta over cosine squared theta times 1 minus, and now I'll have sine squared theta cosine squared theta over cosine squared theta. So I distributed this fraction to each piece inside the parentheses. Now the cosine squareds cancel out, and I do get tangent squared theta minus sine squared theta. Keeping the end in mind really helps you choose a direction to go. Maybe not right away, but eventually, once you try a couple things, you can see where you're supposed to go. Don't get frustrated. Just if you don't think you're getting anywhere with it, start over, try something brand new.